So let's start with upper and lower limits of a sequence of real numbers. Lesson 1. Definition. Let Sn be a sequence of real numbers if for every real number m there exists a positive integer n such that the element of the sequence Sn that should be greater than or equal to m for all n greater than or equal to this positive integer n, then we write Sn tending to infinity, right? And if for every real number m there exists a positive integer n such that this element Sn of the sequence Sn, this Sn is less than or equal to m for all n greater than or equal to n, then we write Sn is tending to minus infinity. So for if Sn is greater than or equal to m, then tending to plus infinity because all the elements are greater than that positive real number m. And if Sn is less than or equal to m, we are saying that this sequence is tending to minus infinity for all n greater than or equal to the positive integer n. The other definition is, let Sn be a sequence of real numbers, and we are defining E to be as the set of all subsequential limits of Sn in the extended real number system. What is the extended real number system? In which minus infinity and plus infinity, these two elements are included in the set of real numbers. So whenever plus infinity, minus infinity, if these two elements are included in the set of real numbers, we say that now this set is extended real number system. And what is the set of all? What is subsequential limit of Sn? Suppose you are having a sequence Sn and it is having a subsequence Sn. If the subsequence of the sequence Sn converging to a point P, then we say that P is a subsequential limit of the given sequence Sn. So E is defined to be as a set of all subsequential limits of Sn. And if we collect all these limits, subsequential limits, and take the supremum of that E, we say that supremum of E is the upper limit of Sn. And if we take the infimum of E, then we say that it is the lower limit of the Sn. And we write limit n tends to infinity, supremum of Sn equal to supremum of E, that is the set of all subsequential limits, which is equal to S star. It is denoted by S star, and for the infimum of E, it is denoted as small s, right? Okay. So let's start with the theorem. Let Sn be a sequence of real numbers. Let E be the set of all subsequential limits of Sn, and S star to be taken as the supremum of E. We have to prove that this S star is actually belonging to E. And the other part, if x is greater than S star, that means if S star is what? Supremum of E. If any element x which is greater than this supremum of E, then there is an integer n such that n greater than or equal to this capital N implies that x is also strictly greater than Sn. So if the x is strictly greater than the supremum of E, that means that x is also greater than the sequence itself, the element of the sequence itself, that is Sn. Moreover, S star is the only number with the properties A and B. We have to prove the uniqueness also. So the first case, we have to prove that this S star is belonging to E. Let's prove this. Suppose in case 1, we are having that if S star is equal to infinity. Now what does this mean? If S star is infinity, that means E is not bounded above, right? What is E? The set of subsequential limits. So if S star, that is the supremum of E, is if the supremum of E is infinity, that means E is what? Set of subsequential limits. if we take the supremum of E, and if that is infinity, then we say that E is not bounded above. Right? Clear? If E is not bounded above, which means the sequence is not bounded above, because E is the set of subsequential of the limits Sn. If the limit itself is not bounded above, the set of limits itself is not bounded above, that means the given sequence is also not bounded above. So if Sn is not bounded above, there exists a subsequence for this Sn. Thus, there exists a subsequence, say Snk of Sn, such that this subsequence is also tending to infinity, right? Because sequence itself is tending to infinity. The sequence is not bounded above, so the subsequence obviously is tending to infinity. Now this subsequence, if it is converging to this point, not point but element infinity, what we can say about this infinity? This will be your, whenever the subsequence of a sequence converging to any element, that element is the subsequential limit of the given sequence Sn. So infinity is the subsequential limit of Sn. And this is a subsequential limit of Sn, which means what is the set of subsequential of limit Sn named as E? So this implies, hence, this is what infinity we have taken to be as S star. We guessed S star to be equal to infinity. So that means infinity is belonging to E, which means S star belongs to E. In case 1, this is proved. Now, if suppose that your S star is minus infinity, suppose. So let S star, this element, to be as taken as minus infinity. Then what can you say about E? When it is plus infinity, we say that E is not bounded above. Now it is minus infinity. And remember that S star is the supremum of E, supremum of all the subsequential limits of Sn. So now what can you say about E? We say that E contains only one element, that is S star. E is having only, because minus infinity is the maximum point, because S star is the supremum of E. That means this minus infinity is the maximum element of all the subsequential limits. If minus infinity itself is the maximum, then what can exist to be as another number with minus infinity? So there can be no other element in that set E. The only element is minus infinity existed in the set E. So we say that then E contains only one element, because minus infinity itself is the supremum element. So what can we think about the other element? They cannot exist, namely minus infinity. Clear this point? So therefore S star equal to minus infinity, it is belonging to E. Clear? Second case is also clear. Now the third case arises. In first case, we take S star to be S plus infinity. In the second case, we have taken S star to be equal to minus infinity. Now let's take S star to be equal to any real number, right? So if S star is any real number, now what can you say about E? Then E will be bounded above. It can be bounded below, it can be bounded above, right? Because now S star is not plus infinity and minus infinity, right? That means E is now bounded. So let's say that then E is bounded above. And we also proved that in the previous theorem that if such thing happens, then E is closed. Okay? That is, if E is a set of all subsequential limits of the sequence Sn, then E is closed. So, and also E is closed. You can check the previous theorems in the previous videos. Now E closed. Now what is the supremum of E? Supremum of E belongs to, can we say that supremum of E belongs to E closure? Yes. What is E closure? E closure is E union the derived set of E. E is the set and E dash is the set of all the limit points of E. Their union is taken to be as the E closure. So obviously supremum of E is the element of E closure. And because E is closed, we know that E is closed if and only if E closure is equal to E, right? As E is closed. Which implies supremum of E is now belonging to E. And what is supremum of E? S star belongs to E. So in all the three cases, we have proved that S star belongs to E. Now the second part, B. What is the second part? Let's check again. If X is greater than S star, then we have to prove that X is also greater than the sequence Sn. Okay, the elements of the sequence Sn. Now if suppose that suppose there is a number X which is greater than S star such that Sn is greater than equal to X. We have to prove this as a contradiction. Let's take the opposite of this and contradict the result. So if possible, suppose there is a number X which is given to be greater than S star such that what we have to prove, that X is greater than Sn. This we have to prove. Okay, let's contradict it such that this Sn is greater than equal to X for infinitely many values of n. Fine. Okay. So then there exists a positive number, actually positive integer n, such that this Sn is greater than equal to X for n greater than equal to n, because it is taken to be as a infinitely many values of n. So now we are having the sequence Sn which is greater than equal to X. So now talk about its subsequence. So therefore there exists a subsequence of Sn thus this implies there exists a subsequence of, let's say, SNK of Sn such that SNK is tending to Y, where Y is greater than equal to X, because all the terms are more than a. Now there exists a subsequence which converging to Y, and Y is greater than equal to X. Thus, if suppose this subsequence is converging to Y, this Y will belong to the set of subsequential limit. This Y is the subsequential limit. So Y is belonging to E, right? And also this Y is greater than equal to X. Further, it is also given that X is greater than S star, right? Which is a contradiction. Why? It is contradiction to the definition of S star, which is contradiction to the definition of S star. Why? Because S star is what? S star is the supremum of E. That means if Y is a subsequential limit, S star is also belonging to the set of subsequential limits of Sn, but S star is a supremum limit, and here it is saying that Y is strictly greater than S star. This is a contradiction to the definition of S star. It should be the highest one. It should be greater than Y because it is a maximum limit. Y is also subsequential limit. S star is also subsequential limit. But here it is saying that Y is greater than S star, which is contradiction. So our supposition was wrong. It cannot be the upper bound now. Thus, there exists a positive integer n such that n is greater than equal to this positive integer n, which should imply that x should be strictly greater than Sn. So our supposition was wrong. Wait. Alright. Now is the uniqueness part. Okay, if possible, we are having two real numbers which satisfy these two A and B part. Right, we have to prove the uniqueness also. So suppose we are having two real numbers which satisfy A and B. So if possible, suppose there are two numbers P and Q which satisfy A and B, and suppose let one number should be different from another now. So let's say that P is less than Q, right? And we also choose X such that we have also chosen X also. We must choose our X. Choose X such that this X is lying between these two numbers. Right? Now, P satisfies B, which means X should be greater than P. Because both the number satisfies A and B. Right? Now, P is satisfying B since P satisfies, let's say it satisfies B part, right? And X is strictly greater than P. So therefore, there exists a positive integer n such that X is greater than Sn, right? For n greater than equal to, and in the P part, it is to be proved that X is greater than Sn. If X is greater than P, then X is greater than Sn, right? P is satisfying the B part. Now, which implies, now see, Sn is from here less than X and X is less than, now X is less than for Q because Q is also satisfying A and B, right? Now X is less than Q is taken from here. We have guessed X to be strictly greater than P and less than Q. From here, Sn is less than X and X is further less than Q, right? Now, for n greater than equal to n. So this implies there does not exist any subsequence such that Snk tending to Q, right? There does not exist a subsequence Snk of Sn such that that subsequence will converge to Q, right? Which implies, now if Snk does not converging to Q means Q cannot be the element of set of subsequential limit. Thus, Q cannot satisfy A. Right? So our supposition was wrong because we have said that both these real numbers satisfies A and B. But from here we are getting that Q cannot satisfy A as it is not belonging to the set of subsequential limits. So our supposition was wrong. Hence, S star is the only number with the properties A and B. Fine, proved. In the next lesson, we are doing one more example, which is very important one. So thank you for this video. Thanks. God bless you all.